Welcome to the Explainer. Today, we're diving into the fascinating world of gases. We're going to look at how engineers figure out what they're going to do, moving from these perfect, simple ideas to the messy, complex reality they have to deal with every single day.
You know, it all starts with the question you might have even wondered about yourself. How can an aerosol can become a tiny bomb in a hot car when the air right outside the car is totally fine? It highlights a really complex problem because the gas inside that can is behaving very, very differently. So what's really going on?
And the answer, well, it gets right to the core of this whole thing. It's all about the massive gap between our simple, neat models of the world and how things actually work. And for an engineer working with gases, that gap isn't just a curiosity. It can be the difference between a safe design and a really dangerous failure. So let's get into it. At the heart of it all is this fundamental prediction problem. Engineers absolutely have to know how a gas is going to behave when you heat it up, cool it down, or squeeze it into a smaller space. I mean, think about it. If you have a solid brick or a glass of water, its density is pretty much a fixed number. You can just look it up in a textbook. But a gas is a moving target. Its density, its volume, it's all changing constantly depending on the conditions. What this means is that engineers desperately need a rule, some kind of equation that can reliably connect a gas's pressure, its volume, and its temperature. This PVT relationship, as they call it, is the absolute key to predicting what a gas is going to do.
And for a long, long time, the first tool everybody reaches for is this beautifully simple equation. You probably even remember it from high school science class. It's the perfect place to start, but it's just a first step.
And here it is, the ideal gas law. PV equals nRT. It's elegant, it's super easy to use, and to be honest, it works surprisingly well. But, and this is a huge but, only under very specific, very limited conditions. And the reason it's so limited is that the whole law is built on a set of perfect, almost imaginary assumptions. It basically pretends that gas molecules are these tiny, dimensionless points that take up zero space, and it assumes they never interact, they don't stick to each other, they just bounce around like perfect little billiard balls. A perfect world for sure, but not the real one. So what happens when we leave that perfect, ideal world and step into reality? You know, the place where all those neat assumptions just don't hold up anymore. Well, the law starts to fail, and I mean fail badly. It happens when you do one of two things. Either you squeeze those gas molecules really, really close together under high pressure, or you slow them way down at very low temperatures. And we're not talking about small errors here. Your predictions can be off by 200, 300, even 500%. An error that big in an engineering project, that can be catastrophic. And it turns out every single substance has this kind of point of no return. It's called the critical point. If you go beyond this specific temperature and pressure, the line between what's a liquid and what's a gas just vanishes completely. It's the ultimate boundary for gas-like behavior. Okay, so if the simple ideal gas law breaks down so spectacularly, what are engineers supposed to do? They can't just throw their hands up and guess. No, they need better tools. They need more sophisticated equations that are actually built to handle the messiness of reality. A classic example is something called the van der Waals equation. The best way to think of it is like a direct upgrade to the ideal law. It starts with the same foundation, PV equals nRT, but then it adds in two crucial correction factors. One of them accounts for the actual space the molecules take up, and the other accounts for the fact that, in the real world, molecules are kind of sticky and attract each other.
And that's really the whole trick. These more advanced equations are so much more powerful because they directly tackle the two big fantasies the ideal gas law relies on. They give you a much, much more accurate picture of what's really happening.
But you know, solving these really complex equations for every single gas out there can be a huge pain. So, engineers got clever. They developed an amazing workaround, a kind of universal cheat sheet that turns a hard math problem into a simple lookup. It all revolves around this single number, called the compressibility factor, or just Z. You can think of it as a reality score. It's a simple ratio that tells you exactly how far your real gas is straying from that perfect ideal behavior. If Z equals 1, congratulations, your gas is acting perfectly ideal. If it's anything else, welcome to the real world. Now, this whole idea is built on a brilliant insight called the law of corresponding states. It's a bit mind-bending, but it turns out that if you scale the temperature and pressure of any gas relative to its own unique critical point, something amazing happens. All these different gases, whether it's nitrogen or methane or carbon dioxide, start to behave in almost the exact same way. They follow the same curve. And what that allows engineers to do is use one single master chart for almost everything. They just find the critical properties for their gas, do a quick calculation to get these reduced properties, find where they intersect on the chart, and boom, they can just read the Z-factor right off the page. It's an incredibly elegant shortcut to a very tough problem.
And get this, it even works for mixtures of different gases. Using this clever averaging trick called K's rule, you can calculate a set of pseudo-critical properties for the entire mixture, and then you can use the exact same chart as if it were just one single pure gas. It's just unbelievably versatile.
All right, so after all this theory, ideal laws, correction factors, Z-charts, let's ask the big question. Why does any of this actually matter? What's the real-world payoff? Oh, it matters everywhere. Getting this right is absolutely essential for things like safely transporting liquefied natural gas, which exists at crazy low temperatures, where the ideal models are totally useless. It's the difference between a high-pressure tank holding steady or failing catastrophically. Heck, even the massive computer models that predict our weather have to account for these real gas behaviors to have any chance of being accurate.
And all of this leaves us with a final thought to chew on. We've seen how this simple, ideal model for gases needs a major reality check to be truly useful. It kind of makes you wonder, doesn't it? Where else, in science or just in life, are we relying on these simple, perfect models when the reality is far, far more complex?